All right, good afternoon. We are making our second pre-AP video for Unit 1, and I'm sitting here at my house trying to be all nice and comfortable on my couch. And my dog has gotten all nice and comfy. She's all comfy too. So we are going to talk about periodic table basics today. And let me get the right screen back again. Here we go. All right, so the periodic table, you've probably seen this before, and I'm sure when you did physical science that y'all learned some things about the periodic table. But so that's what we're going to look at today. If you have your notes handy, some things to remember is that periodic table is arranged first by your atomic number. So it goes 1, 2, 3, 4, and those are the atomic numbers. And we order it in groups or families and in periods or rows. Okay, the groups are the columns going down. Okay, so those are our groups. And then our periods are the rows going across. Okay. Group 1 that I have pointed to right here, these are numbered at the top. As you go across, they have numbers at the top, so you can barely see it, but that little number right there, that is our group number. And the most common groups, there's 8 that are more common, and that they have their own names. So group 1, those are the alkali metals. Group 2 are the alkali earth metals. These are considered the transition metals in here, groups 3 through 12. And then we start over here with group 13. Yeah, these don't necessarily have names. But then we get to group 17, and those are the halogens. And group 18 are the noble gases. Okay, so those are the groups that have just names associated with them. Not all of them do, but okay. So be able to organize or label these periodic table. So if I were to give you a blank one, be able to tell me where the periods are. Those are the things that are going across. Where the groups are. Those are the columns going down. That the first column is the alkali. The second column is alkali earth. These are our transition metals here in the middle. And then halogens is group 17. Noble gases group 18. The symbols, element symbols, are always 1 to 2 letters. If it's more than 1 letter, then the second letter is not capitalized. Okay. So on the left of this little stair step that you see here, that stair step, on the left of that stair step, we have all metals. On the right of that stair step, we have all of our non-metals. So metals are on the left, non-metals are on the right. We call that stair step the metalloids because they have properties of both metals and non-metals. Okay. So remember, groups go down. There's a total of 18 groups. Periods go across, and there's a total of 7 periods. Oops, I don't want that. And there's listed out our metals again and their names. So make sure you know these and you can label them. That is not good. There we go. So those are our groups that you have to know, and you have to know where those groups are located on the periodic table. Okay, element symbols, remember they have 1 to 2 letters. The second letter must always be lowercase, and the first one is always uppercase. Okay, now there are elements on the periodic table whose letters don't seem to match their names at all. So like sodium, Sodium, we think, well, why doesn't it start with an S? It's S-O-D-I-U-M. But when they don't match, like sodium, that's because that name or that symbol came from its original name, which was usually in Greek or Latin or German. In the case of the element tungsten, has the symbol W. That's because the German word for tungsten starts with a W. I'm not sure what it is, but that's where the W comes from. So if the letter doesn't match the beginning letter of the word, the element, then it's probably because that they're taking the symbol from the original name in Greek or Latin or German in some cases. Okay. You do need to know, we are going to have quizzes on the elements, some of the more common elements, because we need to know those symbols, especially like the first 20. And then there's various other very common ones spread throughout. You need to know the element symbol for that element. So we will be having quizzes periodically about on those particular elements. Okay, so kind of start getting yourself familiar with those and being ready for those. We'll start with the first 20. Okay, so going back, looking at the difference between elements, compounds, and mixtures. Okay, so what's the difference between an element, a compound, and a mixture? How are they different? How are they the same? So first off, elements. Elements are, let me make sure this is what I wanted to do today. Hang on. Actually, it is not what I wanted to do today. So we're going to skip this slide and come back to it for day 3. Okay, so let me scroll down here and let's look at, wait a minute. Well, we're going to go ahead and go with it. Hang on. We're just going to go with it. So an element is a pure substance that cannot be broken down into anything smaller and still have those chemical properties. Okay, so its smallest unit of an element is the atom. So gold, for example, I cannot break gold down into anything smaller and still have gold. If I break it down to something smaller, it's not gold anymore. Okay, so an element is a pure substance that cannot be broken down into anything smaller and still have those unique chemical properties. Okay, that's an element. A compound, on the other hand, is 2 or more elements. 2 or more elements bonded together. So water is an example. So we have hydrogen, we have oxygen bonded together. They're stuck together. And that bond gives them unique properties, okay, different from the properties of their elements. Okay, so hydrogen has certain physical properties, oxygen has certain physical properties. For example, by physical properties, I mean those are both flammable. Or actually, those would be a chemical property, I guess. Those are both flammable. But when you put them together and make water, they have some new properties, completely different. Water, which actually puts out flames. Okay, so when 2 elements come together and bond and their chemical properties change, they become a new substance. That is a compound. And a mixture is 2 or more substances that are physically mixed together, but not chemically combined. So they are not stuck together. They are not bonded together. There is no new property that's formed from them being together. They each keep their own individual properties, okay, because they're not chemically bonded together. So we can have heterogeneous mixtures, and heterogeneous mixtures, like you see this candy here, is a heterogeneous mixture. These are mixtures that are easily separated. They're not uniform. They're not all the same throughout. Not everything looks the same. So I can easily look at that picture of M&Ms and pick out all the green ones or pick out all the blue ones. I can separate that mixture out very, very easily. That's a heterogeneous mixture. Okay, it's easily formed. It's not uniform. It looks different, and it can be separated. A homogeneous mixture can also be separated, but homogeneous means the same. So it can be separated. It's just more difficult to separate because it's uniform. I can't see one part from another part. It all looks the same. Okay, so salt water would be a good example of a homogeneous mixture. I know there's salt in it. I know it's salt and it's water, but the salt is spread evenly throughout the solution. And so it's very difficult to tell what part is the salt in versus what part is the water. So it's hard to tell, but I can separate it out. So mixtures can be separated. And they are not because they're not chemically bonded together, and they're just bonded, or they're just mixed physically. They're not bonded. Okay. Particulate diagrams are going to be something that we draw a lot in this class because we're going to draw them in pre-AP. We had a few of them. We talked about solid, liquids, and gases, but we're going to continue that with elements, compounds, mixtures, and different things like that. So an element, this would be an example of a particulate diagram for an element. You can see it's all the same element, all the same atoms, everything's the same throughout there. A compound, here's a compound of water. So we have tiny circles representing the H's, and the big red circle represents the oxygen. And then a mixture is where we have two compounds mixed together. So some part of this mixture is water, while other parts are sodium, and other parts still are chlorine. Okay, so this is salt water. So the yellow ones are chlorine, the green ones are sodium, and the red and white ones are water molecules. And you can see it's spread evenly throughout, but it is still a mixture because these are not bonded to the sodium or the chlorine. So let's look at some examples. So if X is an element, a compound, or a mixture of elements and or compounds. So we're looking just at X right here. So what do you think? Element, is it an element, a compound, or a mixture of elements and compounds? It is an element. X is an element because everything in here is exactly the same. It looks exactly the same. There are 4 atoms of that element, or actually there's 5. Never mind, that should be a 5. There are 5 atoms of that element. Okay, next question. Is Y an element, a compound, or a mixture? So if we look at Y, it is the green and the purple. They are together and they're moving together. So to me, Y is compound. Yes, that's difficult to see, but it is. 2 or more elements chemically bonded together. There are 4 molecules of this compound, and there are 2 different types of elements, 6 of one and 6 of the other. I don't know why they're saying there's 4 molecules. That's a molecule, that's a molecule, 2, 3, 4, 5, 6. So there's 6 green elements and 6 purple elements. So there are a total of 12 atoms, and that would mean a total of 6 molecules. Is Z an element, a compound, or a mixture of elements and compounds? Okay, so Z, the red, white, and blue are all stuck together. So that is going to be, what is that going to be? Very interesting. I'm going to say that Z is a compound. Yes, Z is a compound because the blue, the white, and the red are all stuck together. There are 5 of these, 3 different ones, a total of 15 atoms. Is W an element, compound, or a mixture of elements and compounds? Well, when we look at W, we have a red, white, and blue one. We have a couple of purple and green ones. And then we also have some plain green ones. So this is a mixture of elements, compounds, and compounds together. Okay, so how do we separate these things out? There are 4 basic ways that we separate out mixtures: filtration, evaporation, distillation, and chromatography. So here's an example of filtering. Filtering is separated based upon size. Okay, so the bigger particles stay behind in the funnel or in the sieve, and the liquid is collected as it goes through. So we're separating things out based on whether it's a solid and a liquid mixed together and based on the size of the particles. Evaporation is another way. So like in the case of salt water would be a good example of how we would use evaporation. So all of the water will evaporate off, leaving behind the salt. And then distillation. This is the way that we can separate out 2 or more mixtures, liquid mixtures. So it's separation of 2 or more liquids. And it's separating out based on your boiling point. So you need to think about the best example of this is the good old moonshine still. So if you've watched Andy Griffith lately, good old Otis always seemed to find a still somewhere. And Andy and Barney always were finding the stills and breaking them up. So it's the separation of 2 liquids based on different boiling points. In the case of moonshine, the 2 liquids are water and alcohol. Alcohol boils at a lower boiling point than water. So you take the corn mash and you let it sit there and you let it basically rot, and you put the yeast in it, and the yeast feeds on the sugar and produces carbon dioxide and alcohol as byproducts. Okay. Well, the alcohol is what you want to separate out from the water that's left behind. So to separate that water and alcohol, they would heat the mash solution, okay, in something here. So in this big pot here, you would heat that pot up, and the alcohol vapors, the alcohol is going to boil off first. So it goes up here, and it's going to go through this distillation tube. When it gets to this distillation tube, it's going to begin to cool off because you're not at the heat anymore. It's going to cool off, and that alcohol is going to recondense back down in the form of pure alcohol with no water in it. And so that's how we get the moonshine. Okay. Okay. So moving along. Chromatography is another way to separate out a solution of mixture of solutions of liquids, and it's separation based on solubility, degree of solubility. So ink is a good example of this. Ink is a liquid mixture of different solvents, different dyes, and those different dyes dissolve in different solvents at different places. Okay, so we mix all those colors together and put them in a liquid, and that forms our ink. Well, if we want to know exactly what dye is in there, we put a spot on some what we call filter paper, and so that paper then absorbs a solvent. If that if that ink pigment is soluble in that solvent, it will travel up the paper until it reaches a point in which it's no longer soluble. So that color will come out of the mixture, okay? And then another color will continue to rise up the paper until it is no longer soluble and stays right there at that particular spot on the paper. And then the next pigment may travel on up a little bit more because it may be more soluble in that solvent. So these are the things that are the least soluble because they don't stay dissolved very long. Whereas this is the ink color that is the most soluble because it traveled the farthest up the paper. It stayed in solution the longest. Okay, so we can separate out those different colors. Like black ink is not really, it's not all black pigment. It's actually made up of lots of different colors. And so when that black ink hits the solvent, those different colors that are soluble in that solvent will continue to rise up the paper. The things that are insoluble in that solvent will be left behind. All right, let's look at the difference between physical and chemical properties. Okay, physical and chemical properties. Physical properties are observed without changing the composition of the substance, meaning you don't have to do anything to it. You are simply using your five senses. What it may sound like, what it may look like, what it may feel like, but we never use this one. What it may taste like, but we don't use that one. But that is one of our five senses. So it's what we see, what we might be able to waft, not smell, what we might be able to hear or feel. So some examples are melting points, boiling points, density. Those are all examples of physical properties. Color, texture, state of matter. Is it a solid, a liquid, or a gas? Those are all examples of physical properties. We're not changing it. We're just observing what's going on. We don't make any changes to it at all. A chemical property, on the other hand, is observed when the substance undergoes a change in its composition. So it becomes something new and takes on new properties. I gave the example of water. Hydrogen and oxygen are both flammable. That's a chemical property of those. But when you put them together, you make water, which has a completely new chemical property of not being flammable at all. So that's the difference between chemical properties. Physical properties can be easily undone. Chemical properties or physical changes can be easily reversed. Chemical changes, chemical properties, they cannot be reversed. They cannot be changed. Okay. Oh, sorry. There we go. All right, so let's look at some questions about physical versus chemical properties or changes. Is that a physical change or a chemical change, slicing bread? That is a physical change because we have not changed that substance. Bread is still bread, whether it's in a loaf or in a slice. It's the same as it was before. It may have changed its shape, but it's still the same. So the rusting nails, is that a physical change or a chemical change? It is a chemical change. The nails are no longer iron, but instead they are iron oxide. So you have made a new compound with new properties because they're new substances, new properties. Extensive and intensive properties. I'm going to go ahead and just finish out the notes and y'all can watch this as over the course of several days. Extensive and intensive properties. Extensive properties are things that depend on the amount of something. So they depend on the amount. So we're talking about things like mass and volume. Those are extensive properties. Whereas intensive properties do not depend on the amount. Okay. So things like temperature, boiling point, density, solubility, all of those are things that do not depend upon the amount. The density of water is the same whether you have 10 milliliters of water or 10 liters of water. The density is still the same. The solubility is still the same. The temperature, the boiling point would still be the same. Those are intensive properties. But extensive properties would depend things that depend on the amount. Okay. Endothermic versus exothermic. Remember, endothermic properties, or endothermic means that it absorbs heat. So heat is on the left side of a chemical reaction. You're actually giving off the heat. No, I'm sorry. That is not right. You are actually having to put in heat to get the reaction to happen. That's why I would say it's on the left right here. So for endothermic, it absorbs heat. If it absorbs heat, it actually feels cooler because it's taking that heat in. Okay, so endothermic reactions will feel cooler to your touch because the heat that was on the outside is now absorbed to the inside. Exothermic is a reaction that releases heat. And so heat appears on the right side. It appears as a product. It gives off heat. Okay. So exothermic gives off heat. Just think exit, giving it off. So exothermic gives off heat. Endothermic absorbs heat, takes it in. Okay. Exothermic processes are things like the formation of products or the forming of new bonds is always exothermic. We're releasing energy. So when we put two atoms together to make a compound, that bond that forms between those atoms actually releases energy. Endothermic is breaking bonds. That requires energy. We have to put in some energy to separate those two atoms apart. So if I have water and I want to break the bond between the oxygen and the hydrogen, that's going to take some energy. I got to put in energy to do that. That's an endothermic reaction. But if I have hydrogen and I have oxygen and they form a bond between them, that actually releases energy. So that's exothermic. Okay. During an exothermic process, less energy is required to break the reactant bonds than energy is released to the surroundings when producing bonds, when bonds are formed. So there's more heat that gets released than, wait a minute. Yeah. More energy gets released in making bonds than we put in when we try to break bonds. Okay. Let's see if I can change the color of that, because that is very difficult to see. There we go. So less energy is required to break bonds than the energy released to the surrounding products. Here we go again. Let's change that color so we can see that. In an endothermic process, more energy is required to break bonds than is released when we form bonds. So it takes a lot of energy to break a bond compared to forming a bond. And these energy diagrams just kind of show us that. Some things that you need to know about these energy diagrams is this is the energy that we start with. This is the energy that we end up with. Energy of the reactants, energy of the products. So I have to put in energy to get that to happen. That energy I have to put in is what we call the activation energy. Okay, it's the amount of energy I have to put in to get my reactants to become products. Now, if you'll notice, the products are higher than the reactants. So this is the amount of energy that gets absorbed in that endothermic process. Remember, in an endothermic process, we're taking in, we're taking in energy, okay? So the amount of energy that gets taken in is the difference between the energy of the reactants and the products. For an exothermic reaction, it's the opposite, okay? For exothermic, here's the energy of our reactants, here's the energy of our products. Our products are at a lower energy, We still have to put in some energy to get the reaction to happen right here, but the products are at a much lower energy. So this is the amount of energy that gets released in the reaction. So exothermic reactions release energy. Endothermic reactions absorb energy. And that is the last slide for Unit 1. Okay, so make sure that you have taken notes either on paper or on your notes, however you want to do that. I am going to have paper copies for you, and you can go through these videos and write on your paper copy of your notes if you choose to do that. So if you have any questions, make sure you bring it to class with me, with you, and we will answer those questions in class as we're doing our activities. All right, I hope you have a great afternoon.